Okay, welcome to AP Calculus, Chapter 5, Section 4. I believe there's another day on Section 4. The strategies here, you may want to be going over these. I'm going to be pretty much handling all of these things as I go through this problem set, but all worth taking a look at and coming back. One of the things I really want to point out when we get into our real world problems is finding the domain of a function is really useful, particularly if you're going to calculate. If we know that the domain of the function, let's say x can be values from 0 to 8, then we should set our window x min 0, x max 8, and then anytime you know your domain, go to zoom fit, and you'll see some of that as we go. Critical points, endpoints, so if you're talking about first derivatives equal to 0, endpoints of functions could be solutions to real world problems as well. So lots of stuff in here to go through, but let's get right at it. Example 1, finding numbers. Well, this isn't totally real world. This is pretty much things that we've been doing back in algebra levels. But it says the sum of two non-negative numbers is 20. I actually need a little bit of room for these two parts. So I'm just going to call that A plus B. Those are my two non-negative numbers whose sum is 20. And then it says find the numbers if the sum of their squares is as large as possible. So that would be, I'm just going to call it S of AB is sum of their squares, A squared plus B squared. So we've got two equations here, or we've got a function and an equation here. Basically, we'd rather have this as just a function of a single variable. So I would say choose the easier variable to solve for. In this case, it doesn't really matter. So I'm going to say A is equal to 20 minus B, and that means that A can be replaced by 20 minus B. So I've got a function now. My sum of the squares, just based on B, is 20 minus B squared plus B squared. Now at this point, we could actually, if we didn't have to show work, didn't have to show calculus, we could actually go and graph this function and try to interpret it. But we're going to go through the calculus process here. I'm going to do a little simplifying. S of B is, if I FOIL this, I get 400. I get minus 40B. I get plus a B squared out of this foiling, and I get another B squared, so plus 2B squared. Or I get 2B squared minus 40B plus 400. Okay, so that is our sum of the squares just based on B. The first derivative of that is simply 4B minus 40. And what we most typically do is we take first derivative, set them equal to 0. So I'm just on autopilot right now. 4B minus 40 equals 0. Add 40, divide 4, B is 10. If B is 10, when B is 10, A is 20 minus 10, so A is 10. What we need to consider here for our critical points of this is where the derivative is equal to 0 and our endpoints, because this was differentiable everywhere. I don't have any other critical points other than that. So this would represent our critical point where the slope was 0 of the derivative, or our derivative, excuse me, was 0, and slope is 0 of the original function where it levels off. And our endpoints, well, if I have two non-negative numbers add up to 20, then A, for instance, could be 0, or I'm going to go with B since we have this. B could be 0, B could be 10, and B could be 20. And we need to consider our areas for each of those. So if I put 0 into my area formula here, I get 0, 0, 400, 0. I get an area of, 0, 0, 400. I get an area of 400. If I put 10 in here for B, I get 400 minus 400 plus 200. And if I put 20 in here for B, I get 400. I get another, if I put 20 in here, I get 800, I get 1200 minus 20 in there, therefore I get another 400 here. You can go through that and find that. Okay, the sum of their squares is as large as possible, as small as possible. So here's the sum of their squares. So this would be small, B is 10, A is 10, and area is 200. And our largest would be when A is 0, B is 20, or A is 20, B is 0, and that area, and that area would be 400. Okay. All right, then part B, one number plus the square root of the other. So that's going to be, I'm just going to call it R of AB. One number plus the square root of the other number is as large as possible, as small as possible. So A, again, can be replaced by 20 minus B. So R based solely on B could be 20 minus B plus square root of B. I'm going to write it as B to the 1/2. And I'm going to go ahead and find that derivative. R prime of B is 0 minus 1. This would be plus 1/2 B to the negative 1/2 would be that. Well, what do we do with derivatives? Negative 1 plus 1 on 2 root B is 0. So I get 1 on 2 root B wants to be 1. If I flip both fractions, both sides, or cross multiply, I get 1 equals 2 root B. Root B is 1/2. So B is square 1/4. So B is just 1/4. Be interesting to look at that on a calculator. Perhaps we'll do that in just a moment. If B is 1/4, then A must be 19 3/4. And then we can come up with our final solution here for R of AB by putting those values in, or we could put just 1/4 in here, and we get 1/4. That's 1/2 plus, so R of 1/4, that would be 1/2 plus 19 3/4. That would be 20 1/4. And what are we dealing with here? Just numbers, so 20 1/4. Okay. Now, other things we have to consider. How about, so we've got R of 1/4. How about R of 0? So R of 0, when B is 0, I get 0, 0, we get 20. And how about R of 20, our endpoints, when B is 20, I get square root of 20, or 2 root 5. This would be our maximum choices, and here would be our minimum, and that would be when B is 20 and A is 0. Okay, let's take a look at this. I'm going to look at this function right here on graphing calculator and start talking about that process. We've got some more freedoms with graphing calculators for checking. So I'm going to go into y equals, clear that guy out of here, and let's get this kind of darkened a little bit so it'll be easier for you to see at home. So we've got the function 20 minus b, or x, plus square root of x. And what I'm interested in, here's where we go back up to knowing the domain. My b values can run from 0 to 20, and once I have those in place, I'm going to zoom fit this. So that's zoom 0, zoom fit, we got it going right here. And it looks like we have a decreasing function over that range, but if you look real closely back here, close to 0, it appears like maybe it goes up a little bit. So I'm going to go second calc value. Let's check endpoints. That's easy enough. 0 is 20. I like that. Or 0 is 20. Let's go to 20. and we get 4.47. I assume that's the 2 root 5 or square root of 20. And then I'm going to do second calc max. Second calc max. I gotta zoom all the way back over here. Probably should have thought that through first. I'm sure you guys know there's a quicker way to do this, but let's get back to 0 here. So at 0, I'm going to stamp it, and I'm going to go a little bit till I think it's coming back down, stamp it, and I get, looks like that would want to be 1/4 and 20.25, and there we have it. So calculator is going to be helpful for us for checking, but we're still going to be responsible for showing our calculus along the way. At least we're freeing up calculator for you, which we haven't done in the past. Okay, minimizing perimeter. What is the smallest perimeter possible for a rectangle whose area is 16? So I'm just going to draw a picture of it up here. We have, say, A by B, and we know that area equals 16. That means that area based on A and B is A times B. So we've got that to work with, and we're interested in the perimeter. Our perimeter based on A, B would be 2 A's plus 2 B's, but back to here, I know that the area is fixed at 16 equals AB. Solve for the simple to solve for variable, either one's the same, so I'm going to say A equals, divide, equals 16 on B. Okay. Therefore, A can be replaced by that. And then I get perimeter just based on B is 2 times 16 on B, 32 on B, plus 2 times B. Making our first derivative. This is 32b to the negative first, negative 32, b to the negative second, plus 2. If I set that equal to 0, find a critical point, negative 32 on b squared equals negative 2. That would be b squared equals 16, and normally b would equal plus or minus 4, but only positive 4 makes sense to us. So we have critical point at b equals 4. We also have endpoints for b, or do we? Well, b has to be at least 0. In fact, you'd argue it has to be bigger than 0. It can't be 0 and still have an area, and it can approach actually infinity. B can get as tall as it wants if a gets close to 0. So we don't really have endpoints to consider here, and that's probably why we're just asking for the smallest perimeter. Let's think about this just for a second. If a was 4, b was 4, our perimeter is 16. If a was, let's say if a was 8, we'd be 8 and 2. Now our perimeter is 8 plus 2, 10, plus another 10, 20. It's going to get bigger and bigger. I mean, a could be 1,000 if b was a tiny fraction, then it's 1,000 back, and our perimeter is more than 2,000. So our smallest perimeter perimeter based on A, so when B is 4, that would imply A is 4 as well. Our perimeter based on A and B is 2 times 4 plus 2 times 4, or 16 inches in this case. And what's the smallest perimeter possible for a rectangle whose area is 16 inches, and what are the dimensions of the rectangle? The dimensions are 4 by 4 inches. Okay. Describing rectangles. The figure shows a rectangle inscribed in an isosceles right triangle. So here's our rectangle inscribed in isosceles right triangle. And I know that this rectangle, we don't really have to put this in here, is 2x by whatever height we have here. Starting to get a little lag, so I'm going to stop after this problem. But they ask us first, express the y-coordinate of P, express this coordinate in terms of x, which they didn't give the hint. Now, since this is it tells us up here, isosceles right triangle, these distances are the same, making these angles the same, making these 45 degree angles, meaning this slope is -1. And if this is 45 by 45 and this length is 1, this must be 1. So we're up 1. So the equation of the line from B to A is y equals -1x plus 1, which means this point P is really x, -x plus 1. All right, where does that take us? Express the area of the rectangle in terms of x. Area in terms of x, then, of the rectangle would be 2x's times the height, -x plus 1, or -2x squared plus 2x, which we know is an upside down parabola. So the anticipatory question is, what would be the max, and this is the area of the rectangle, what would be the maximum area? What is the largest area of the rectangle and what are its dimensions? Endpoints for x would be 1, but if we went out to 1, the rectangle would have no height. 0, if we went to 0 for x, it would have big height but no width. So we're only looking for where this parabola levels off. A prime of x equals -4x plus 2. If we set -4x plus 2 equals 0, we get a critical point at x equals 1/2. When x equals 1/2, y equals -1/2 plus 1, or 1/2. So what are the dimensions of the largest area, and what are the dimensions? I'm going to go dimensions first. Our dimensions, if x is 1/2, we're 1/2 this way, 1/2 that way, and if y is 1/2, we're up 1/2. So the dimensions of the rectangle, what is the largest area the rectangle can have, and what are its dimensions? Our dimensions would be 1 by 1/2. Do we have units here? No units. Okay, and the area would be, here's our area, or here's our area, either way. Our area would be -2 times 1/2 squared plus 2 times 1/2. That's -2 times 1/4, -1/2 plus 1, 1/2 square unit. 1 by 1/2, sorry, 1/2 square unit. Hopefully you can follow back on that. 1 by 1/2 units for the dimensions, area 1/2 square unit. Okay, so I'm going to pause this one and hopefully we can get that lag situation taken care of before we move on to the second half.